Welcome everybody. I'm just going to give it a minute here to let everyone sign on. Thanks for joining us. All right, great. I'm just going to get started right away just because we have a lot to cover. So thanks everyone for joining us today. We're here with Rob Pope from Ecolighten to talk about the HVAC guide for Part 9 homes and how you can use it in your new builds and retrofits. So just move forward to the next slide there, Rob. All right, thank you. So I just like to begin today with a little territory acknowledgement. So the Community Energy Association, we acknowledge that we carry out our work on the traditional and ancestral territories of Indigenous peoples. So through our commitment to truth and reconciliation, we support First Nations, Inuit, and Métis communities in taking climate action and reaching their goals of energy sovereignty, security, and resilience. So I'd just like to begin our session today by acknowledging the Indigenous peoples from all of the diverse and beautiful places we're joining from. So I'm joining from what is now called Nelson, but for thousands of years has been the traditional homeland of the Snaiks Nation, the Silks Nation, and the Ktunaxa Nation, and is home to the Métis and many diverse Indigenous peoples. So I'd like to acknowledge with deep respect and gratitude that it is in thanks to their generations of stewardship that we're able to enjoy these mountains, forests, and waters in the way that we do. All right, just the next slide, please. So just a quick introduction to the Community Energy Association in case you haven't joined us on one of these webinars before. So CEA is a BC-based nonprofit. We've been working for over 25 years with local government and Indigenous communities across the province with the goal of reducing emission, conserving energy, and helping progress us to a low carbon and healthy future. And the next slide, please. So the Kootenay Clean Energy Transition, or CES, is a project that was developed to address shifts happening in the energy efficiency, renewable energy, and home comfort space. So through CES, we want to help Kootenay and boundary communities prepare for a more energy efficient and healthy future through training and capacity building sessions like this one. So thanks to the generous support of the organizations you see listed at the bottom of the screen there, we're offering this free webinar as a part of that training and capacity piece. So today's webinar will be shared and recorded with all of you, and you can also find it on our website just at the bottom of this slide there, the communityenergy.ca/built environment. And then just the last slide there, please, Rob. So this is the first webinar in a series. So we do have a few other webinars coming up. I'll make sure to put the links in the chat kind of when I'm finished talking here, so that you do have to register for each webinar separately. So if you are interested in joining us on any of these topics, just click the link in the chat and we'll see you next month or the following. And then so that's it for me. I'm going to pass things along to Rob, and we do encourage, if you have any kind of questions going through, go ahead and raise your hand. We like to take questions as they come through, or you can put them in the chat and we'll have time at the end of the session to address your question as well. And I'll pass things over to Rob Pope. He's a wealth of knowledge. We're really lucky to have him here today, and take things away.
Thanks, Jenna. Hi, everybody. We'll just get right into the meat of this. On the agenda, we'll put the material that we're talking about into context, how it was developed, and the structure of it, and in closing, the takeaways. So let's get started right on it. So this is a CSA document. So this was developed over quite a long period of time with the idea in mind that we need to fill a gap in the industry across the country in Part 9 buildings, specifically residential construction and also in retrofits, because there is not a unified, verifiable, agreed upon set of standards of practice, right? So we put that all together into this guide, and this is what we're going to be talking about. Just to be clear, this is a CSA group publication, so it's not just wouldn't this be nice, everybody read this, here's some ideas. It's an actual formal document that has been put together with the intent of it becoming required practices. The objectives, awareness, first of all. It's a pretty fragmented industry across the country, and here in BC is no exception. Um, the if you go from jurisdiction to jurisdiction, there's differences in how they apply standards, whether they even apply standards at all. You know, they don't verify systems. There's no design guidelines, that kind of stuff. And some and others there are. It's all over the place. So what we want to do with this guide, wanted to do with this guide and are doing is creating awareness across a whole spectrum of stakeholders. So building officials, EAs, mechanical contractors, builders, architects, homeowners, everybody. Um, in this guide is an outline of best practices. It's not, you know, extremely detailed like the ASHRAE standard for commercial projects, for example, but it's what is the difference between no practice, good practice, and best practice for HVAC systems. Practical application. So this is coming from us and all our stakeholders that were involved in this, and all the agencies, governments and utilities and so on that supported this. This is supposed to be practical. It's not just theoretical, it's practical. And also the idea of it is to build confidence that we can do this. You know, as an industry, we can create established standards and find the tools and processes to verify those standards. As I said, this is for everybody in the industry, all stakeholders, so builders and developers, architects, designers, building officials, HVAC designers and HVAC contractors, energy advisors, utilities, homeowners. So anybody that has any skin in the game in the building of a new house, and to a lesser degree, this guide addresses the retrofit of HVAC designs into an existing home. As I said, this was published through the CSA group, it's Canadian Standards Association, so it's an official document. And it was done with the funding of BC Hydro, Fortis, BC Housing, and the City of Vancouver. So thank you to them. The Development Committee, we give you an idea, it was pretty onerous. It wasn't easy. You know, we created the document out of work that we had done for years in the industry. We basically put together all what we consider best practices, and then with the agencies supporting us, the funding agencies, we reached out across the country to get subject matter experts and stakeholders. So that included, you know, government, utility, policy managers, and so on, engineers right across the country, designers. Included agencies like NRCan, BC Housing, provincial government, City of Vancouver, City of Richmond, BC Hydro, Fortis, Manitoba Hydro, HVAC DC, which is a national organization of HVAC designers, BCIT, CSA, and BOABC, building officials. So we met, let's go back this slide. We met every 2 weeks to update all the stakeholders and then get all the feedback and make edits and make sure everybody was on the same page and that we all agreed on what was the content of it. And the reason this is, and I alluded to it earlier, is because we have a kind of a pretty big gaping hole in the Part 9 building industry. Unlike commercial buildings where, you know, you have engineers and there's processes and verification and sign-offs and schedules and all that kind of stuff. And it's a very routine practice in that part of the industry. In residential, we don't have such a thing. And so that's been an issue, and it's been an issue for, you know, for decades, obviously. But it's become very, very critical in the last number of years because of the changes to the way we build and the technology and the demand and climate change and all those kinds of things. And in that context, you know, a typical home these days does not include adequate consideration for the mechanical design up front, which is a big issue. Not only do we not have a standard for what a design is, we don't even have a design, right? Most cases, which is a problem. And that creates issues as limited design choices, additional costs, um, performance issues, and of course, frustration and for homeowners and builders and everybody, and liabilities. Um, if the, as the homes have become more energy efficient, higher performing homes, oversized HVAC equipment and poor design is emerging as one of the most serious issues in residential construction. And this has been borne out by research, not just here in Canada, but all across North America. Same issues apply in a lot of the American states. And it's become such an issue that it's gotten the attention of not just building officials and jurisdictions, but industry as a whole. You know, there's been all kinds of incentive programs and that kind of stuff, and then they measure the performance after incentives to see where are we gaining efficiencies, reducing energy consumption, all that kind of stuff, and discovering, hey, wait a minute, it's not happening. Why not? Right? Well, it's not enough to just give an incentive to say put in a higher performing piece of equipment in your home, or build your home better and put a heat pump instead of a gas furnace in there. um, the metrics for seeing the improvement in energy reduction hadn't shown up. And so the question was why? And then the research happened, lots of it. And granted, an awful lot of the results from that research was already known in the industry. And it's that, you know, it's one thing to put nice equipment into a house that's efficient and everything, but if you don't install it correctly, or you don't choose it right, you oversize it, or you don't design the distribution of that energy adequately, you're not going to get optimization from the system. And so the so agencies, governments, and utilities discovered all that, but also warranty providers getting issues, from their um, the those who they insure, are we're coming up with these issues quite a bit, and also manufacturers getting warranty requirements, warranty requests. Um, so all of these conspired together to create a sort of kind of a perfect storm a few years ago of say, oh, okay, let's get this sorted out. And we're in that process right now, and this guide is part of that. There's kind of three things, kind of like a 3-act play, really. Three general um, processes that are required to ensure a properly installed, executed HVAC system. And it starts with load calculations. Unfortunately, even though it has been required by code, it hasn't been enforced. Load calculations don't get done as it is required by code, which is a certain standard of measuring heat loss and heat gain that's verifiable. It's called F280. That's rarely used. It's changing, granted, right now, but still the majority of calculations are rule of thumb. And of course, that's not great. Design, more coincidental than coordinated. From the contractor's point of view, mechanical contractor, HVAC contractor's point of view, usually the situation is the house is built, the structure's up, then you get the call to go and give a price. By then you've missed so much opportunity in designing a more appropriate system for that house. And then finally, commissioning. If you've done your load calculations and you've done a great design, now you got to execute it. And the only way to know that it was executed well enough to meet the design intent, of course, is to check it. And unfortunately, that doesn't happen often enough. That's the verification part, making sure that all the systems, the system itself in general, and all the subsystems within it are all working properly, all configured right and customized for the application it's in. Best practices is you do the load calculations. More and more jurisdictions are requiring it, which is good, but it still has a long way to go. It's already in the code that you're required to do this. There's a CSA, again, set of load calculations that's been verified not only by very smart people making doing the math and physics to make sure that there is a methodology that is accurate, but it's been tested tens of thousands of times, if not more, in actual applications over the last 10 years or more. The more since 1912, this one came out as the most current one. There's been so many of these that it actually works, right? So that's pretty important. HVAC design, we're going to talk about this a little bit later. What we're really talking about is integrated design process. That means don't wait till it's too late. Do all your planning, your thinking, your strategizing, what's the best system to put in and how to design it in a way that it's going to work and everybody's going to be happy. Do that upfront with all the people that have some skin in the game. You know, the builder, the homeowner, if you can, developer, structural engineer, whoever it is that will have some impact on decision making at the early stage before you start building. That's ideal. And finally, verification. That's the startup performance documentation, testing, and all that, and the handover to the client. Some of the evolving practices that's happening in the industry would include blower door testing. Now, there's a lot of jurisdictions across the country where you're required to meet a certain air change and infiltration rate, right? And the only way you're going to know if you did it or not is to do a blower door test at the end, right? And that has been a requirement in a lot of jurisdictions for a long time. But what has started to become a requirement and what's always been good practice is you test it mid-construction so that you don't have to worry at the end when everything's painted and maybe the furniture's already there. If you fail at that stage, at the final stage, then it's a catastrophe, right? So do it before cover up, before cover up, so that if there's any issues, you can deal with them then. You can fix anything at that point. So mid-stage blower door testing is evolving as a standard of practice, and it's also going to be evolving, as it is in some jurisdictions, as a requirement. Standardizing HVAC compliance. Remember I said the standards, where there are standards, they're all over the place, right? Different documentation, different requirements, different jurisdictions. And that's one of the ideas of what we're going through now with this Better Building Practices document. And the processes that it's going to be leading to is to standardize. So everybody is looking at the same permit requirements, information checklists, verification checklists. All the tools are the same. They're not all over the place. Harmonizing the standard itself and the ways to verify it. And also inspections. That's an evolving process. An awful lot of jurisdictions don't have experts on HVAC as inspectors. You know, some do, but very few. And or they don't have the resources to develop that skill set within in-house. That is changing. Well, we need to support authorities with jurisdiction with the right tools and methodologies for doing at least the bare minimum inspections to ensure that the installation meets the design intent, that whatever you submitted as a design actually got installed. The industry is changing, as I said before, you know, we have regulatory changes, climate change related. We have evolving technologies driving changes. We have homeowner demand driving changes, right? So you think about it, the new national model codes, even though it's an incremental approach, tiered codes, it's across the country, it's changing things, right? It's making us approach building differently. Climate change is impacting us because it's you know, on the regulatory side, it's changing how we do business. It's making us adapt our practices to meet compliance requirements, to reduce GHG emissions, for example, right? That's not a kind of a natural, spontaneous industry evolvement. That's as an interjection from government. We also have, we're talking about national, provincial, and in a lot of cases, regional governments, right? You, in many jurisdictions, you've got different process regulatory requirements. You've got even complementary incentives from other jurisdictions. So it's across the regulatory board that these changes are happening. Technologies, you know how it is. If something better, newer shows up, you might want to consider using it, right? And that's what's happening in the HVAC industry. It's better technologies. You know, we got cold climate heat pumps now, which alleviates the issues with whether a heat pump can work in cold climate, which is most of our country. We have better efficiencies with our technologies. We have smarter controls. You know, so we can't ignore that that is driving changes as well. We have to, as an industry, learn about these technologies and integrate them into our markets in a way that's accessible for the end users, the homeowners. Consumers are getting smarter and smarter all the time. Now, part of that is dangerous because an awful lot of information is coming from the internet. And so you know how it is. And if you don't put all that information in the right context and and avoid the fake news part of it, you can get pretty dangerous as a consumer. So it's really important for the contractors to be smarter so that they can sense check that kind of information. But what it does, it creates a discussion. You know, what about this? What about that? Can I have that? You know, so that's changing the industry. And in addition to that, there is an awful lot more consumers. We see it in our own business. It's changed dramatically. The volume of our clients that are genuinely interested in reducing their carbon footprints and are willing to do what it takes to affect a positive change in that way. So, you know, they'll spend more money, you know, sacrifice the countertop in some cases, you know, that kind of stuff. That's happening more and more and more, right? And that's forcing us to change how we approach doing HVAC systems as well. So three things, you know, the regulatory environment, changing technology, and consumer demand. We're kind of in a little bit of a renaissance in this industry, whether we like it or not. It's happening. In respect to harmonizing the standards, so first we got to create the standards. We've done that. We've got to make sure everybody accepts those standards, that we're doing that. And then we've got to have tools and methods of verifying that those standards were met. And that's in process too. And as you can see here, this is just a few documents, of which there are many. In other words, the process is already out there. These documents already exist. They're accessible to the industry already. We just need to use them. To take on an HVAC project for residential, it doesn't matter what kind of house it is, whether it's multi-unit or it's a single detached, whether it's a fancy custom home or it's a market built home, doesn't matter. This applies to all residential, that you need to go through a process that has these stages. Stage one, discovery. We'll talk more about each of these stages as I go through the slides. But discovery is what it sounds like. You need to discover a few things. What's the budget? What's the incentives? What's the imperatives on the job? What's the critical imperatives that's driving the project? Stage 2 is load calculations. We touched on that already. We'll talk more about it. Stage 3 is equipment selection based on stage 1 and 2. And then from there you can go to an HVAC design. From there to the quality assurance piece, once it's designed, you want to make sure that it actually got executed properly. Then finally, or sorry, not finally, the performance verification, which is checking to make sure all the systems are set up right and are working, hitting their performance targets, and finally the handover to the homeowner. So let's start with the discovery. Usually, as I said before, we'll do things in residential construction in a linear way. You don't call the HVAC contractor until the building's up, which is way too late. You want it when you've got the idea for the building, at least the HVAC designer, at the stage where the decisions you make are going to impact what you build. You want that up front, not as you go. The intended consequences of that linear approach is silo-based thinking, uncoordinated objectives, inadequate focus on the home as one entity, the whole building approach, and of course, unrealized opportunities, missed opportunities. A job is finished, people living there, and then you got the should have, could have kind of thing going on. You want to avoid all that, and that's, you'll hear this term a lot in the industry, integrated design, IDP. It's just a fancy terminology for just get everybody together up front that has some impact on how it turns out, and work it out, coordinate, collaborate, get all the ideas sorted and nailed down so that when the final set of plans is done, it includes everything you need to know. And now you just got to follow it. It can be if there's a homeowner, then ideally the homeowner would be part of that engagement. Obviously a builder, you might have an architect or interior designer or a house designer. That would be good. The mechanical HVAC and energy advisor, pretty key. Sometimes you might have a structural engineer, sometimes you might have an interior designer. Doesn't matter. Whoever it is that has some impact on that process should be involved. You can see the graph on the right here. You spend less money up front on that linear approach, right? But you lose it by the end of the project. You spend more money up front on the integrated design, but you gain it back on all kinds of other things. Not your building schedule, materials used, costs of systems, changed work orders, all that kind of stuff, and you get better value as well. So the discovery, one of the things that I think is really critical, especially where there's a homeowner involved, but if it's not a custom home for a homeowner, there's somebody has something at stake about how the home is built. And in a lot of cases, it's the developer. They know their market. They know who the demographic is going to be living in their home. What we want to know is all of that stuff. We want to know, the occupancy lifestyle. Are we building for, a couple without kids, or is it a big family? Is it retired? Are they, are we building resilience in for climate issues like forest fire, smoke, and that kind of stuff, or not? What kind of air quality should we be thinking about? Naturally, budget, that's a big one. Of course, we want to find out what the budget is, what the expectation is, sense check it, and to make sure that we're not missing opportunities. Sometimes that'll involve, pretty easy to do cost benefit analysis. No, I think I'm happy to take questions as they come up.
We do have a question that's come through here. Sebastian has a question.
Sure.
Go ahead and unmute yourself, Sebastian, or I can just read it from the chat. Okay, so he asks, you keep mentioning that there are missed opportunities if the HVAC is not designed early on. Can you give some examples?
How much time do you have? Geez. Well, one of the things that I do, and I do too much of, I guess, and have done for decades, is going around troubleshooting issues, resolving HVAC systems that are not working to the expectations of the homeowners. And so what we see is, missed opportunities is, they wanted um, cooling, they didn't get it. That's a big one. That happens a lot. Um, or um, the distribution of the systems not well. That room above the garage, it's cold all the time. That or the attic or the loft, the top floor, is too hot all the time. There's those kinds of systemic issues or system issues. I mean, but there's also you go into houses and you look at bulkheads everywhere that didn't need to be there if it was worked out in the first place. You can imagine, right? It's not just an aesthetic, which is important to a lot of people. It's also, all of that bulkheading costs money. You got to frame it and finish it and all that kind of stuff. It didn't need to cost that much money in a lot of cases. So it's the aesthetic is missed opportunities. It's also things like, if you if you there's an awful lot of situations where simple things like joist directions can change because the span is fine either way, but the difference it makes to hiding your HVAC is profound, right? A simple little change could really make a big difference. That's a missed opportunity if you don't work that out ahead of time. Um, there's I probably have I could probably do an hour presentation every day for weeks on all the photographs I have of the issues that have come up because they didn't get it sorted ahead of time. And there's an awful lot of those missed opportunities. Sorry for the long-winded answer. I hope that's okay. I'll move on. When we're doing discovery, before we get started, we want to know, like, what's the strategy? How can we develop a strategy without knowing a few things? And so this is a discovery. And one of the other things we want to know is what's the intended energy performance? Is it we're trying to reach, like, for example, in BC, step code 3, 4, 5? Do we want to build a net zero ready, passive? What is it? What is it we want to achieve? Or do we just want a minimum compliance, right? So that's another thing to figure out. Fuel source system, depending where you are in this country, in BC, it's no different. You might be in an area where you don't have natural gas. And so, you're stuck with what? Diesel fuel, heating oil, electricity, heat pump. It's an option, right? It's not across the board always one best route to go for your fuel source. It depends on a lot of things. And of course, quality assurance. What do we need to do to get the permit? What is it that we need to inject as a design strategy to just get approval for compliance? Once we got all that, those building blocks of discovery, then we can move on to the next, right? We then have an integrated design process started. Discovery is the start of that. And we can move forward to coordinated design, because we haven't finished the process yet before building. We still need to articulate that strategy. And we'll get onto that in a minute. The next step for the mechanical designer, contractor, is to do the load calculations. With that, you have nothing. Without that, you have nothing. Everything builds on those load calculations. If those load calculations are incorrect, everything else is going to fail because of it to some degree or another. And you used to be able to do rule of thumb more reasonably accurate back in the day when houses were all leaky, and so you could just look at that house and it would be probably not much different than the last house you did and the house before that. But these days, you can't you can't tell anymore, right? Depends, because there are so many performance attributes to the home in terms of its insulation, infiltration, what kind of solar gain you have in the windows, U values, all that kind of stuff. What you can have the identical looking house hit a number of different step codes. You know, it can be that same house that step one could look no different than the house that's net zero, right? So rule of thumb doesn't work, and you got to get it right, and you got to do load calculations. If you get it wrong, not only does the system fail in many ways in terms of performance, you know, you get reduced efficiency. If the system is oversized, it's going to short cycle. It's going to reduce its like the life cycle of the equipment and be uncomfortable. And you've also spent more money than you needed to, and there's no benefit to that whatsoever. There's no upside to avoiding load calculations. And load calculations pretty straightforward. What we want to know is how much heat is lost in the winter, for example, and how much is gained. Um, and one is the heat gain, one is the heat loss. And it's impacted by things like the insulation, uh, window U values, solar heat gain coefficient, how leaky the house is, infiltration, internal loads, all these things are taken into consideration. There's two general ways of approaching heat loads. In new construction, you have to do room by room. And you have to use the standard. It's called F280, F280-12. It's in the National Building Code. It's also in the BC Building Code. The other way to do it is a block load, just the whole house. And that would be a recommendation for a retrofit, for example. You don't have to. It's nice if you can, if you've got the resource, time, and the money to do it, to do load calculation broken down room by room in a retrofit, but block load is adequate. But a new construction, because you're designing the delivery of the heat and cooling, you really need to do room by room by room. Another load calculation methodology, but is not CSEP 280, and it has a different purpose and is often confused with CSEP 280, is HOT 2000. HOT 2000 is what the energy advisors use to determine the performance attributes of the home, the energy performance attributes. It's an energy modeling program. It's what it's intended to do. Enercan, that created the program, doesn't like you to use it as a design tool. They want you to use it just as an energy modeling tool only. However, the results between doing a HOT 2000 energy model, the whole building, and the results from simultaneously and in parallel to it doing the CSA F280 heat loss load calculations should have at the end result a very similar result. You should be within 10% or less. And it's a good way to verify. You can't use the HOT 2000 to design your system, but what you can use it for is to look at the load calculations and see if they're close enough. And if they are, then it's all good. But if they're not, if they're out of that variance range of 10%, then you know something's not right. One of them is off. One of them has the wrong inputs or assumptions about assemblies. And that's when you got to say, oh, wait a minute, and get those two entities together and sort out why there's a variance. We did what we call a sensitivity analysis. So imagine this house was actually built in Kimberley in BC. They built it to step 5, which is pretty impressive considering the climate and the style of the house. But what we modeled it in every form you can imagine, step 1, step 5, in every climate zone in the country. We manipulated the information in this house so many ways, can't even count. And you can see this exact same house in different climate zones, most of which we have right here in our province, right? How the impact of the climate zone changes the heat loss and the heat gain, right? You know, obviously, and anybody will know intuitively that as a colder climate, more heat loss. And similarly with the heat gain. Um, so this was done with code minimum, these numbers. Same house, different climate zones, different outcomes. With medium performance, so we went, I think from step 1 to step 3, or maybe step 4, I can't remember. The loads changed. Same house, exact same house, same climate zones, load changed pretty dramatically. You can see here. I don't expect you to, to look and digest all this at once. This will be available for you anytime. But suffice it to say that we know the house didn't change one bit, not a single thing. It looks exactly the same. It's just different compliance requirements, and the loads changed dramatically. And then we did the same thing with high performance. So, for example, step 5, and the house comes down quite a bit in its load calculations, heat loss, especially. What doesn't change as much when you insulate your walls better, you reduce the infiltration, make it less leaky. These kinds of things all have a great impact on the heat loss of the building, but doesn't affect the heat gain that much. It does affect it, but not as much as most people think. We'll talk about this in a bit. So here's some graphs. You can see on the left, as you go from high performance or base code to high performance, you can see it clearly illustrates that the heat loss is going down, right? You have less heat loss because you have a better performing home, right? But look on the right here, the difference in the heat gain is not that much. One of the reasons is at the bottom, I should have put this at the top. At the bottom of this slide here, you'll see that we fiddled around with one thing, and that is the solar heat gain coefficient of the glass. That has the largest impact on the solar gain, or the solar gain, which impacts the heat gain. The numbers are between 0 and 1. They're really a percentage, right, of how much coating is on the glass. So you can see that we've used, everything else is the same. The USI is 1.6. It doesn't matter. We took 3 different numbers, 0.25, 0.4, and 0.6 in this house, and just saw what would happen if we changed the coating on the glass. This is the coating that filters the solar gain, the solar waves coming through the glass, and therefore the solar gain in the house. Because you remember, it doesn't matter how energy efficient your opaque assemblies are. In terms of heat gain, everything stays the same. You still have the same amount of people in the house, lights going on, cooking, and all that kind of stuff, right? That doesn't change. What does change is how much gain is coming through your glass. That has a large impact. And the solar heat gain coefficient base 0.6, which is kind of clear, like a passive home window. You have the 30,000 BTU heat gain. That's what you need in energy to keep the house at a comfortable temperature. You reduce that to 0.4. It's still clear from your naked eye. You wouldn't see that filtering on the glass. You reduce that load by 22%. Now this is for a standard orientation. If you change that orientation where you've got lots of southern exposure, western exposure, those numbers are amplified. They're more dramatic. If you go down to 0.25, which is pushing it a little bit, because that's when you start to see the tint on the glass, that grayish greenish stuff. And that's when you need to manage expectations about that. For a lot of people, it's perfectly okay and so good. We'll go down to 0.25 on the glass. But if you want to stay above where you start to see that tint, you want to be in a 0.3 range or a little higher. We find the sweet spot to be about 0.32, 0.33 in that ballpark. And we also find that any manufacturer of windows is able to provide that.
Rob, I just want to give you a time check here as you
Sure.
flip between slides. It's just 8:45. So you
Wow.
have 15
Okay.
minutes.
Okay. I'm going to move a lot faster. Equipment selection. So once you've got the load calculations, you got to select the equipment, and it's pretty important. There are third-party agencies that evaluate equipment, test it, and so on, and verify capacity and efficiency. You got to check those. You don't want to depend on the manufacturer's literature alone. That's important to get that as well, right? But you got to select equipment based on the require capacity to keep the home comfortable. It's also, considering energy source. Is it a gas or not? Is it a hybrid system or not? That you should have sorted out in the original discovery. Operating costs and benefits, of course, that should have been sorted out in the initial discovery. So by the time you get to this stage, it's about selecting the equipment that meets the capacity and efficiency requirements. And they're all different. Even manufacturers models within their own catalog, each model will be different. You got to check the third-party ratings and the performance characteristics of each equipment so you get the one that's appropriate for the project. We have two general types of distribution systems, as everybody probably knows. One is a radiant, typically in-floor radiant system, which is common in the Lower Mainland, has been for quite a while, still is very common, but changing now. It's becoming more about forced air, and of course forced air systems, which is the typical system across most of this country. When you're considering equipment choices, you want to look at obviously equipment that you can get in the market area. We do work all over the place, and there's places where you can't get that product. You can get an equivalent, something else. Make sure it's something that's available in the market you're in the region you're in, that has distribution support, technical support, and that the contractors install it and know the product and have relationships with it. That's pretty important. And then all the other things is about, you want to get stuff that's not too noisy, of course, and that meets what we had already discussed, the capacity and energy efficiency requirements. Ventilation and indoor air quality. I think it's insane to think about building a house these days without an HRV or ERV, right? There's other ways you're allowed to do it, other compliance paths, but they're unbalanced. It's ridiculous to even have them available as a compliance path, and I think that's not going to last too much longer. So I don't want to spend any time on those paths. You need an HRV, simple as that, or an ERV. Either one will do, and that balances the airflow and recovers the heat, right? And it keeps the house breathable, fresh, and prevents it from getting stale. Domestic hot water, there's a few choices. These days, we're not going to see that picture on the bottom anymore with the draft hood, old conventional gas hot water tank. We're going to see heat pump hot water heaters like the other photograph. On demand ones, if the house is, the demand is small enough, because there's a limitation what you can do with on demand. You got to be careful about that. Electric water tanks, nothing wrong with them. There are some really good quality ones out there. There's a few choices with domestic hot water. From an HVAC designer or installer point of view, typically you're just specifying the equipment to fit the energy compliance requirements and design strategy of the house from an energy point of view. You're not really designing the plumbing too much, but that is also an option, is to design the plumbing as well. What is a forced air design? Here's the critical things that it includes. An appliance selection worksheet. How did you decide what equipment, what performance curves, fan curves, all that kind of stuff? So there's that, the appliance selection worksheet. There's a few forms that you can use for that. Equipment submittals, dimensions and that kind of stuff, and nomenclature, so you're ordering the right models. And a schematic arrangement of the forced air. systems, fittings, airflow, CFM per branch, all that kind of stuff that you need to put on the document that is called your design, how you arrived at those numbers. And of course, you want to draw it out in a way that's it's clear where all of the pipe is going and the duct is going, and making sure it doesn't go through beams and that kind of stuff. And also your airflow targets. You got to register in the living room on the west wall. How many CFM are you expecting to get out of that grill, so that you can check it at the end to make sure you got it. At the beginning, you know what you need, write it down, and at the end, check to see that you got it. It kind of, I mean, it doesn't have to be pretty, but it has to be articulate enough that it's clear, right? You can have single line drawings. Some designers do single line, 2-line designs. And in a lot of cases, you might have 3-dimensional. The picture on the right with the 3-dimensional looks pretty fancy. It's for a big house, right? But it's becoming more common. And I think 10 years from now, people will be doing nothing but 3D because it's a lot more accessible. It doesn't cost that much. It's not enough to draw it out where all the ducting going and what size it is. You need to have with that design what is an acceptable standard practice. What gauge of pipe to use, how to hang them, you know, all the things that surround where you put the ducting should be included in that, and that is how to do the ducting. And details. And a lot of times you look at a set of plans, you go, oh my God, there's so much clutter here. What you want to do is turn that clutter into clarity by doing sections where you're required. And you want an equipment schedule that says, the make, model number. You also want the electrical loads for the electrician and any other notes. You've got an air handler serving the, the basement living in rec room, for example. You want that note on there, what the equipment is doing, what's the model number and manufacturer. The hydronic design, that's like what we talked about, radiant heat pump. It's the same. You're just adding a few more things, more detail about the pump, pipe sizing, pump curves, and that kind of stuff. I won't get that into it too much, but suffice it to say, it's almost the same. There's a few differences. Primarily loop layouts in the floor that's going to be covered by lightweight concrete of some sort of topping, manifolds, that kind of stuff, GPM, pressure drops, all that. So there's a standard approach for what that kind of design looks like. And it'll have a schematic, this is the hydraulic schematic, how all that water is moving, all that liquid is moving. Ventilation design. For example, if you had a radiant system in the house, all you have there for in terms of piping and ducting is your HRV design. It would look similar to a forced air design, there's less of it. And it would need to meet either section 932 or F326. Those are optional compliance paths. It would look something like this here for a ventilation layout, not much different than the forced air. Once you get all that, what you end up with is something that everybody's agreed on. And then now you can have, you can put it out for tender. You can have 3, 4, 10 contractors if you like, all bidding. They're all going to be bidding on the same thing, right? And so you don't get this, contractor A says I need this, and contractor B says I need that, and you get different prices, different ideas. You got an apple, and instead of an apple and an apple, you get an apple and a banana and a hammer, right? It's very confusing. At least this way, everybody knows what the intent is and what they're bidding on. So you get fair pricing that way. It's not enough to do a design and then the HVAC contractor starts working on it. You've got to make sure everybody surrounding that HVAC contractor also knows the design. Where's the framing? You want a grill, for example, end up under a window, right? You want the framer to know, leave that spot, start your centers from here, or adjust that spacing in the choice so that, you don't get asymmetrical outcomes. The simple things like that. Making sure the plumber knows, don't run it down the center of the room. I need that for the trunk line for the HVAC. Everybody surrounding that can impact the execution of that design should be coordinated. Field reviews. So you got the design, you install it all. Somebody has to go and look at it. Ideally, there's a separation between the designer and the HVAC contractor, right? But a builder can do this. A inspector can do this. This is ideally what we'll end up with, is to look at the design on the one hand and look at the installation and make sure that it's following the design. Performance verification at the end, I can't state enough how important it is. It is so critical. The equipment leaves the factory, has no idea where in a planet it's going to live. It's just default settings. You have to configure it, set it up, and test it. And you want to do the shakedown anyways before the homeowner moves in to see if there's any component failures that are warranty related, for example, right? Or you missed something, but now you can fix it. You want to get it working, checked out, everything sorted out before the homeowner comes in. That verification is a process, and it's a process that requires the right tools and instruments and procedures. And once that's done, it should all be documented, recorded. There's a lot of documentation available, a lot from the manufacturers directly in their own startup sheet requirements, but also from different agencies that give you nice document tools to check off whatever kind of system you're putting in. And that's what you're seeing here. And then finally, once you've done all the verification and you know it works, now you can do the handover to the homeowner. And there's a lot more to it than is apparent, because these systems are getting more complicated, right? And so you really do have to educate the homeowner. This is how you program the system, help them out with it. These are what you can do, what you can't do for setbacks, for example. Here's the filter, here's where you change it. Make sure you clear once a year the pine needles off that outdoor unit, and have a maintenance regime available, because it's just like a car. You want to check it once in a while, make sure everything's okay, and keep it optimized. You also want to make sure all the documentation is available for not just the homeowner, but for future technicians, so they can come and see what's in, what was the baseline that we started with, and what's different, right, if there's an issue. And you also want that paperwork for warranty. This guide is available through these. I think you'll all have this available to you. So there's access for this guide through these websites, these portals, I guess.
Great. Thanks, Robin. Yeah, we'll make sure to share those links with everyone. And I will say, I know we kind of went through the performance verification piece a little quickly there, but we will be joining Rob again to talk about that piece in more detail. So as I mentioned, I'll follow up with the links to those individual webinars. So if you want to learn more there, let us know. And recognizing we are at time, thanks, Rob. That was so much information to get through in just such a short period of time. But if there are any questions, I don't see any new questions in the chat. I think they've all been addressed. But if you do have any questions, feel free to raise your hand. We can take a couple of minutes to answer your question here. No, we're just getting some thank you. All right, I don't see anything. Oh, okay. Are there any standards for retrofits?
Good question. No, that's it's pretty frontier there. There's being developed though. There are standards that are associated with certain incentives, like BC Hydro, for example, or Fortis. To qualify for the incentives, there are some very minimal performance standards that have to be third-party verified, but not generally. There isn't. The only standards are for parts of retrofits like the gas or electrical. You need an electrical inspection if you're changing something in the panel, or you need a gas inspection if you're changing, if the equipment is gas. But they don't, neither of those inspections look at the whole system.
Great. And Sebastian asks, with the air tightness, would you put a return air in each bedroom or a ventilated door?
You have to have either. It'd be nice to put return air in every room, but that's costly and it's hard to do. So a combination, you have to have at least a 1/2 inch undercut in doors that can close, where you have central returns. You need at least return on each level. That's the minimum. And if you can get more, especially in master bedrooms, if you can get one in there, that's pretty critical. But getting one in every room would be nice, but it's not practical all the time.
Great, thanks. And Sebastian, you still have your hand up. Did you have a follow-up question to that, or was that? Oh, okay, perfect. And then Rod asks, I've heard that in-floor heat pump systems are less effective at cooling. Curious to know what your experience is with this.
There's no difference as long as you get the right heat pump. So what we have is two types of heat pumps in that regard: air to air and air to water. Right? They're both heat pumps. They have the same kinds of performance efficiencies and attributes, but you got to choose the air to water heat pump if you want to do radiant. And then that air to water heat pump is going to deliver your heating, whether it's in the floor or in air. It can do both, right? Because it's cooking water, and you can put that water through a fan coil or straight into a radiant floor system. It's just as effective. It's no different from an efficiency point of view. You can even do cooling because that heat pump can chill water as well as heat water. So you can put that into a buffer tank and deliver it through fan coils and get your cooling out of it that way. You can do a little bit of radiant cooling. It doesn't do the whole load. There's no all sensible load. You'll meet only part of it. So somewhere between 8 to 12 BTUs per square foot. But it doesn't touch the latent load. You still need air for that. You need to condense that humidity somehow. Otherwise, you'll get cold and clammy in the building.
Okay, perfect. Great. Rod says thanks. Any other questions for Rob as we wrap up here? I don't see any coming through. Great. Well, you have Rob's contact information there. So if something comes up, feel free to shoot him an email. You can let me know. Thanks so much, Rob, for joining us today. And thanks everybody for taking time out of your morning to be here. We'll hopefully see you next month. And yeah, enjoy the rest of your day.
Thanks very much. Thanks, Jenna. Thanks, everybody.